everyone, and welcome back to Astronomy Arcade. My name is Victoria, but you can call me Vicky. But today, you can still call me Vicky. But today we also have a special guest.
Hey, it's me, Sig of Skeptical Sig fame.
Yes, we have Sig here joining us today because Sig is a NASA Solar System ambassador, and we've been in talks for a little while since you got the position about having you on the channel and talking about some science stuff, talking about some
Yeah,
astronomy.
yeah. I got into the Solar System Ambassadors program about 2 years ago or so, and it's a program out of NASA JPL where it's like a 1,300 person large volunteer corps of just educators, and you can just it's like very unguided. You could just apply your trade in whatever way you want, and some of the ambassadors are like actually chat with politicians,
That's
which is
very cool.
wild. Uh, and For me, I just like going to like libraries or wherever small settings to go teach. So
Yeah.
um, yeah, it felt like a natural continuation after COVID was winding down to pick back up. Because before that, I was a docent at a museum for a while.
Oh,
Um,
nice.
yeah, Specifically the Denver Museum of Nature and Science was the most recent one I was a docent at, but
Oh, okay.
always just sort of teaching. I think my first teaching role was I tutored kids in calculus when I was like 16 or so, uh, and that was 14 years ago. So I've been teaching for a while.
Yeah, you got the teaching bug. Yeah,
Yeah.
I feel like especially people in at least the people that I know, Pablo is here.
Oh yeah, there's also a Pablo.
We have a second special guest. We have two special guests. Pablo is also here, and he's so sweet. He's so cute.
Yeah.
We'll talk more about Pablo later too. Um, Grant's excited about seeing a dog. But yeah, I feel like there's like a lot of people in astronomy and space science specifically that get that are very compared to the other sciences, like very interested in specifically like community education and outreach stuff.
Mhm.
And it's super cool that NASA has a program where it allows you to do that along with however else you're working in the department or industry, I suppose.
Yeah, in the
But
industry.
yeah,
Yeah, it is really cool. And they also like it's not just like a the sail to catch the wind of all these educators, but they also sort of provide some opportunities for engagement. So they're like, okay, so for our NASA Solar System ambassadors, this coming Thursday, we got an astronaut to talk to you, and he's going to talk about this specific mission that he's working on. Oh gosh, bye. Okay. Or like, uh, you know, the project scientist for a particular mission will come on and give us a talk, or someone who's working on the latest soil samples from Osiris Rex will come on and give a talk about their findings. And so
that's very
it's like
cool.
educate the educators, and then also let them, force multiply uh, that information. So it's a
Yeah,
really good program.
that's really cool. Sorry about that, by the way. I had to move the microphone a little bit because I realized I'm much more angled this way today, and it hates to stay plugged in. Uh, but but yeah, so I guess that's a little bit about the NASA Solar System Ambassadors Program. But should we start by talking a little bit about yourself, how you got into astronomy originally, and
Yeah, so I'm from Orlando. That's where I was born, and in the late '90s and early 2000s in Orlando, prime viewing for the space shuttle launches, absolutely prime viewing. So like you couldn't, it was not a phenomenon you could ignore when they're coming into land at Kennedy Space Center. They'd be breaking the sound barrier over your house.
that's crazy. That's
So
wild.
quite an obvious sign of spacecraft to space flight nearby. Um, and then also, as we're talking about before, this through line of people who want to do community education existed there as well, in equal numbers. And so uh, being able to go to Kennedy Space Center and just like see all the space stuff, that was sort of like the early nudge. And then I don't know, I was always sort of the weird kid at in the elementary school that was like reading some of the textbooks in fourth grade that no one had ever checked out before.
Oh, we have one checkout on this book. My friend's actually it's so funny. My friend's a librarian right now in a like it's a K to 6, and
Nice.
she does a purge of the books every once in a while, and she's like, there's been one person that's checked out this book 6 times in the past like 5 years, and no one else, and she's like, I think I'm gonna just give it to her. I feel like that was little Sig, just like, I want
Yeah.
this textbook.
Yeah, from there, I don't know. I got an education in it. My undergraduate degree was in engineering physics. So at Embry-Riddle, that took the form of like half space physics and half spacecraft design, which is really cool. It was like a sort of like an applied physics for astronomy program, if that makes sense. And
Gotcha.
then my master's was in spacecraft systems engineering. And well, I use both of those degrees on a regular basis. And
There you go.
I think if you include like the area of concentration and minors and all that stuff, the word space just appears in my in my degrees like 4 times or 5 times.
I love it. Just so you know, it's
Space,
definitely space.
space, concentration in space.
Lots of space.
Yeah.
Nice.
So I currently work at the Space Telescope Science Institute, which is based out of Baltimore, but it's a basically just a NASA contractor. NASA founded the institute to handle science operations. So that's like, okay, where the rubber meets the road, how do we execute on these different like scientific inquiries on our telescopes?
Hmm.
And so NASA was like, hey, we'll just stand up an institute and fund this institute instead of managing that team in house. But of course, NASA has seats on the various committees for time allocation, et cetera, et cetera. So it's an interesting part of the ecosystem, but it really is where scientific inquiry meets satellite operations. And I feel like for me, that's sort of what I've been interested in. The early part of my career was with, we'll say, a defense contractor, a nameless defense contractor, for 6 years and change.
I
And
mean, that happens with a
hey,
lot of astrophysics. I feel like it's that's an avenue.
yeah, I
I
think I
get it.
think Neil deGrasse Tyson wrote a book on that. It was like,
Oh, really?
yeah, like astrophysicists and the defense industry, or something like that. I
It's
wonder if it's on my bookshelf. I might have gotten rid of it because it was too much for me.
That's
It's too
fair.
close. um, but yeah. But I found myself really enjoying the like satellite operations part of that job, and so when I found satellite operations, meets astrophysics, right, found myself right in the middle of that Venn diagram. I'm like, absolutely, let's go to Space Telescope. And also, I work from home, so
That's hell
it's an
yeah.
absolute benefit for that.
Love that. Yeah.
So,
So
yeah, one last thing about the Space Telescope Science
yeah.
Institute. So, we host the Science Operations Center, which again is like where the rubber meets the road. How the astrophysicists send in their inquiries to like experiments to be done in the telescopes for the Hubble and the James Webb and the Roman spacecraft. The Roman spacecraft going to be the bulk of what we talk about today because
Yes.
that's what I work on, and it's going to be launched next year sometime.
Very exciting.
Um, so the science operations for those three, the flagship telescopes, and then indeed the actual mission operations center for the James Webb. So if you ever wanted to go and figure out, where they sending commands from, it's the third floor of my works building.
Very cool. That's awesome.
Yeah, it's really
And
cool.
remind me, I may be getting this wrong, but is this the group that also like the organization that was started by Dr. Roman, or is that a different one?
Indeed.
It is.
Yeah,
Okay.
yeah, yeah. She was definitely a part of this vision for having an independent institute. Because like one of the benefits is the United States government, and by extension NASA, can't be like directly petitioned by, we'll say, foreign actors necessarily.
Hmm.
And it just got like really messy for if you want to do this in-house, how do you like build that framework in a fair and just way?
Yeah.
And one of the other things that, Dr. Nancy Grace Roman, um, I guess if you want to shoot yourself to slide 6 if you're sharing
Oh
stuff
yeah.
yet. But I also have a
Let
chart
me
deck that
set
I,
that up.
I presented at the local library like 2 weeks ago that we can
Yeah.
we're using as
Let's see.
a visual reference. But Dr. Roman, just very inspiring figure. I really, 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 really respect this person. Let me a little digression here. Like I watched a lot of like interview footage because she passed away in I think 2018 or so.
Yeah.
So I watched like a lot of interview footage that NASA had with her, like when she was only 92 and
Only
still
92 and still working and like doing stuff.
yeah yeah
It's
yeah.
crazy.
And like the interviewer asks Dr. Roman in this video, like, so uh, you were the first director of astronomy, and that's like a pretty important role in NASA's history. Did you have any role models growing up? And then Dr. Roman's just like, no,
Yeah, I mean,
just
yeah,
like
it's like
so
I
savage.
you're like I did the I was the first one to do the thing. What do you mean? Like I
Yeah, yeah.
It's me.
Yeah,
I'm the
so
role
brutal,
model.
so honest, just like no, I'm the role model, exactly.
Yeah. I love that. Honestly,
um,
yeah.
yeah, so it was like, so she was NASA's first director of astronomy, and not first female, not first, asterisk, just first director of astronomy. NASA said, hey, let's start doing astrophysics, and they hired her to manage that department. Incredible.
Awesome. Yeah.
Um, and as part of that, she like set the vision and the precedents that NASA should serve the astronomical community in its astrophysics, not just NASA's interests. So
Yeah.
that when they're doing observations on the observatory, um, that they should be soliciting input from anyone who has an interesting idea. Um, and so that was what, sort of, yeah, that mindset, that sort of cultural declaration sort of kicked her into understanding that, yes, we also just need an independent institute. Because if someone from like, you know, someone from North Korea, to use a random country, wants to like do an observation on our telescope, they're allowed to.
Yeah.
It's a competition of ideas.
Exactly.
um, but if they were petitioning NASA directly, it just raised a lot more questions.
Yeah, there's more politics involved and this
Exactly,
allows a little
exactly.
bit more of the science to take precedent, which
Yeah. So the Roman Space Telescope was initially W first, which was a telescope recommended in the National Academy of Sciences 2010 Decadal Survey. And W first was like wide field infrared surveyor telescope, probably is what that acronym stands for. And then after she passed away in 2018, we really recommended that we rename the telescope after her.
nice.
Yeah.
So I suppose we can jump into the telescope. Is it my slide previews are very small because of the way that I have it set up, but number 5 I think is your first like the overview sort of.
Yeah, yeah, yeah. Go to
Okay.
that.
Let's switch over to that.
So the sort of let's just give you like the salesy taglines to understand why this telescope is going to be really really impressive.
Yeah.
Uh, so maybe we'll talk about it in this way. The Hubble Space Telescope has been operating for 35 years. So it's been up there for a long time.
Yeah.
It's so long.
It's
And
crazy.
like my direct coworker like helped launch the Hubble, and he's just like,
Really?
yeah, yeah, yeah.
That's cool.
Um, you just can't replace that sort of like, well, I've been here the whole time level of knowledge.
Exactly. Yeah. I know everything you could possibly know about it.
Exactly,
It's like, oh,
exactly.
okay, cool.
Um, in the 35 years or so, the Hubble has downlinked about 200 terabytes of data,
Jesus.
which is a lot of data. That's a lot of data
Well, wait,
over
you said,
35
I'm sorry, you
years.
said 200 terabytes?
200 terabytes.
That's okay. In 35 years. Okay.
Yeah,
You say that number,
modest.
and I'm like, that's a lot. And I'm like, it's not
35
that
years. I don't know. Okay. Um, yeah, Grant, it is one of the longest still operating objects in orbit.
It's
is the way
crazy.
I'll
Yeah.
this is the way I'll agree with your sentence. Um, yes, the Hubble, which has fundamentally changed our understanding of the universe in so many different ways. From the deep field to some of the first transiting exoplanets to so many ways that it has updated and informed our understanding of the universe. in those 200 terabytes over 35 years. The Roman will be downlinking about 20 petabytes in the first 5 years,
Oh my
about
God.
one and a half terabytes per day. We
That's
expect to pass the Hubble's 200 in the first 6 months or so.
Oh my God. That's insane. That is insane. I mean, that's just if anybody wants like an example of like how data like capacity and storage and like transfer has evolved so
Yeah,
fast.
so fast.
Perfect
Yeah, if
example.
you shoot over to slide to 10, there's I don't know a visual representation of like
Oh
this
yes.
difference. Um, but one of the reasons why you need such a large amount of data is that the Roman Space Telescope is a surveying mission and not like a framer, not like a pretty picture necessarily. You're not going to dedicate our time onto one object. We are surveying broad parts of the sky.
Hmm.
Um, oh, Pablo.
He's
Pablo thinks
so
it's data
cute.
talk. uh,
Hi, Pablo.
Look at this little man.
Oh my goodness, he's so cute. Oh, I love that he's in his little sling.
Little papoose.
Yes.
Sorry, what were we talking about?
No, you're good. You're good. I've got the big data slide up.
Oh, yeah, yeah.
And then we were
Yeah,
talking
and so
about just
that's
how much. Yeah.
20 petabytes of zeros and ones. This isn't even like the higher level scientific processing on top of that. And so our server that hosts, is called the Roman Research Nexus. The server that hosts this scientific data processing, because for this mission, we can't rely on astronomers having enough processing power to actually do the analysis that they're interested in
Yeah.
doing. So we offer a cloud-based research server. That server is rated for 8 exabytes of data. That's
What even does that mean? What does that
eight
mean?
8 million terabytes of data is what it's spec'd for, and we think that's what we'll need in the first 5 years. It is just so. Oh, and by the way, this is at the same resolution as the Hubble. This information,
Oh my God.
ridiculous, absolutely ridiculous.
Wait, so
Um,
like where does this get stored? Like where does it
I'll give you one guess as to what company is doing it for us.
is it Google?
Amazon.
Okay. It's gonna be one of those three. It's like Google, Meta, Amazon.
Yeah. Exactly, exactly.
That makes sense.
Yeah, I guess we go to the next chart. This is a really small one. I apologize for how small it was, but um, so backing, still under this premise that Dr. Roman set out when she became the first director of astronomy, uh, is that we should be serving the community, and so this telescope um, has 3 core community surveys. Has 2 instruments on board. One is the primary instrument, and then the secondary instrument is a technology demonstrator. Maybe we'll save at least 10 minutes at the end to go over that one because I think that was
Yes.
really exciting.
I did have questions about that too. I was interested in
Okay.
that. Yeah. So, but we'll come
Um,
back to it. Yeah.
yeah. Yeah. So when we were soliciting input for how to define these community surveys, this is sort of like this is the word map. This is what people were talking about and interested in their like maybe twice an abstract length, maybe half to a full page description of what their scientific inquiry was. And that's
Yeah.
over 113, pitches that, passed muster that were like, okay, this person understands astrophysics and is asking interesting questions. We're actually stacked, and these are the topics. And so there are sort of three, there's sort of yeah, I don't know how to describe them, so I'll just list them out. Uh, there is what's called a galactic bulge time domain survey. And so that's just pointing, near Sagittarius A, near the very center of the Milky Way, and looking at how stars evolve, or at least we'll talk about transient events evolve there. Maybe this is a good time to maybe compare it to, James Webb and Hubble one more time. Uh, the Hubble Space Telescope, is mostly dedicated for this like public inquiry, and so of the time allocated for that, maybe out of 365 days in a year, maybe there's 300 days on the telescope for observations, and you chop it up and allocate it to people who are asking interesting questions.
Yeah.
So when you solicit proposals in what's called the cycle, this is run cycle 4 or cycle 5 now.
Yeah,
Uh,
something like that.
cycle 5 just I think cycle five's number just got published actually.
Oh, okay.
Uh, for the for the James Webb, it was 9-1 oversubscribed, meaning that there for every 10 proposals, one gets accepted and nine get put on the bench.
Yeah, I remember seeing that. I was like, Jesus.
Jesus. And
That's fun.
Hubble, James Webb, big, beautiful, flashy machine. The Hubble, 35 years old and, experiencing its, aged symptoms, 7-1 oversubscribed. So for
Oh
every
my
eight
God.
proposals, seven are benched. Yeah, yeah, ridiculous. Absolutely ridiculous.
Yeah.
These telescopes are in such demand. And, the Hubble is still the best ultraviolet imager that we have.
Hmm.
The James Webb, clearly the best infrared imager that we have. And so Roman, but what they're doing is they're like looking at particular objects and characterizing them pretty well. Roman's just like bah, 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 clear in the sky.
Yeah.
Uh, Maybe if you go to slide 9 and zoom into the left side, we can get an idea of
Is it gonna let me
um,
zoom? There we go. Zoom into the left. Oh, with the wide field
yeah,
instrument?
yeah, just
Okay.
just really accentuate that.
Yeah.
So all 18 of those boxes, that's just like the primary instrument. That's one instrument, one picture looks like the image within those 18 boxes. And then on the bottom are the Hubble Space Telescope's two instruments and then the James Webb's infrared camera. I want you to notice the subtitle under the middle one. That's the HST WFC3.
Hmm.
That's Hubble's wide field
Oh.
imager. To our wide field. Like I said, just ridiculous amounts of data.
Yeah.
But one thing you can do with one thing we're planning to do with our telescope that you just can't really do at scale with these other telescopes, besides the obvious things, is time domain science. So if you're asking to do, I want to see how this field, this scene, evolves over time. It's not just like you're taking one picture and you're done. You have to revisit that multiple times. And all of a sudden, like for this one proposal that wants to do time domain science on this thing, you're throwing away dozens of other proposals. And so that like balance never made sense for Hubble or James Webb. Like you're always just, it's really hard to justify time domain science. Now we have dedicated surveys for that to do the time domain science. And the stuff we're looking for is exoplanet transits and micro lensing events. So those would be like if there's any, solar mass, not supermassive, but just solar mass black holes, they would make the light waver in interesting ways. Um, yeah, so we expect to see plenty of that in the center of our galaxy, and the ability to revisit this area over time is what's going to give us that information. So I think we have like in the first 5 years something like I don't know 300 days worth of observing in the galactic bulge. And so that's like the center of our galaxy. If you imagine our galaxy like I don't know, like a pancake in this, then the high latitude areas are like the North and South Pole.
Yeah.
Um, and so our other surveys are both in the high latitude areas.
Got you. Okay.
So the Milky Way filled with dust, you really can't see stuff behind it.
Hmm.
Uh, but if we're looking to observe distant galaxies, for example, we'd be using these high latitude areas. And so we have a high latitude wide area, as the name suggests, this is like a broad canvas of the sky, and then a high latitude time domain. So in this high latitude, just staring very deeply into the same spot over time and revisiting it to see what we see. And we're expecting to see a lot of like supernova, and especially like type 1a, which is like the standard candle supernova. Um, I don't know, and other galactic changes. One of the things that we're most excited for with the high latitude domain surveys is we want to see dark matter's microlensing effects as well. Uh, and so let me see if there's a good chart here. Yeah, maybe 15. Um,
15. All right.
uh,
Sorry, I've been having my mic muted a little bit because they've
no,
decided
you're
that
good.
right now is a great time to take out the garbage and just rattle every piece of metal outside. Uh, but
Yeah, so
okay.
like so we expect to see the like background light of galaxies and stars sort of warble around a little bit,
Got
and
you.
being able to characterize that quote warbling is one of the goals, and we expect to be able to map that specifically to dark matter content uh,
Okay.
along the at least along the optical path, and maybe build more evidence for the existence of dark matter and its structure throughout the universe.
Mm-hmm.
Hopefully, we'll
That
see.
sounds very interesting.
So like uh, maybe just like a brief discussion of gravitational lensing. Like there are wonderful examples. If you go to the next slide of like strong gravitational lensing,
Mm-hmm.
so that image in the middle of the slide, there's just sort of like two galaxies that are like along the same line of sight. This like blue galaxy, which appears like a horseshoe or like a ring around
Yeah.
that center node, that's a normally shaped galaxy. That just looks normal wherever it exists. But because there's such a huge object in front of it that is pulling its gravity, like, is changing the path of light around it. Um, this is like a strong gravitational lensing uh, event to
Mm-hmm.
like really truly distort the way that the galaxy looks behind it.
Yeah.
Um, that is like this is a prediction that Einstein made that you would be able to see these things with a strong enough telescope, and indeed he was right. Turns out he was right about some stuff. And this
Yeah.
was one of the things he was right about.
Shocker. Yeah.
But the effects of like dark matter we were expecting to be a lot more subtle.
Yeah.
And so the way I like to think about it is like if you had a big swimming pool and you had just like one drain right in the middle, you expect to see just a huge whirlpool. Is quite clear, is quite obvious. That's the strong gravitational lensing.
Mm-hmm.
If you just had like, I don't know, some wind on the surface of your swimming pool and it was just like not
Yeah.
like not like crazy, it's just a little more subtle. Yeah. And that's one of the things that we hope to be able to figure out with the high latitude surveys.
Very
So
cool. Very
ah,
interesting.
I can go on forever. There's so much to talk about.
No, I love it. I mean, I feel like the dark matter stuff is like there's so like as far as the questions that we get from people that are like interested in astronomy and to a level that like we usually talk about on stream and stuff. Dark matter
Yeah.
is the thing that like everybody's always interested in, and I think it's just exciting to hear that like there's something that is specifically also like working with that with the gravitational lensing and stuff, and figuring like trying to figure that out, and knowing that astronomers are very interested in this as well, because it is one of those things that like obviously there's a lot of stuff that we still don't know or don't fully understand, but like that's one of the huge ones of like we don't like we need to research this more, and it's so exciting that Roman is like
Yeah.
really
Just
focusing in on that.
it's a line item, like we are expecting to figure it out.
Exactly, yeah.
Amazing.
Gonna figure
And like, hey, guess what, Vicky? If we don't see this sort of warbly effect, that means we were wrong about dark matter.
Yeah, which is also insane in itself. Like that's like a whole other yeah.
Yeah.
Yeah. Then it's like, oh, okay. So
Yeah, like both the positive and negative result cases are interesting.
exactly. So it should be cool. Also, real quick, just a reminder, I guess, to everybody in chat. Feel free to ask any questions that you have about the Roman or about Sig's work or anything like that. Just pop them in there. I have the chat open, so I can field those. But yeah,
Yeah, happy to answer questions.
Yeah.
Or tell you that you asked a good question and I don't know the answer to it. Also happy about that. um,
So,
yeah.
just to clarify, going back to the where did it go? Did it disappear? Where did I was looking for the slide with the wide field instrument explanation.
Right.
So, you said about like 300 of the days of the year it's going to be doing the wide fields, right?
This
Or
would be yeah, so I guess let me see.
okay.
So for the galactic bulge time domain survey, uh, it's 438 days. For the
Oh
high
wow.
latitude, it's 180 days, and for the high latitude time domain is 180, and the high latitude white area is 520 over the 5 years.
Okay,
So
gotcha.
uh, yeah, I have like these like the we'll just say the flyers,
The flyers.
uh, if you will, on like page like slide 13, for
Oh, okay.
example. Uh,
Oh yeah, there it goes. Okay. So 12% of the entire. Oh, I see. I looked at this before and I was like, "What is this showing me?" But it's one of the what do they call it? Because that
celestials.
yeah, celestial sphere. Oh yeah, yeah. So this is a great slide example for seeing exactly how much the Roman is going to be covering, which is crazy when you think about it. Because like the
Yeah,
you look at like a JWST image, for example, and it's like the tiniest fraction
yeah,
of this.
absolutely.
Yeah. And whereas the Roman's just gonna just see
Broad
everything.
strokes.
Yeah.
You want it, you get it.
Exactly. Which
All this data is going to be public. Like you just have to register for an account. Uh,
really,
you could just go in and pull whatever data you want. That's still
that's
true
awesome.
of the Hubble and James Webb too.
Yes.
Uh,
Yeah. Do they still I thought JWST had some
I
like
think I
a
know what you're about to say.
release thing or
We call
something.
it a proprietary
Yeah,
period.
yeah, yeah.
So, so yeah, like yeah, the like, hey, all these people are proposing for time on the telescope. They get the rights to that data from their proposal for about a year
Okay.
um,
Yeah, yeah.
to write their papers.
Hmm.
Uh, because one of the things to think about is like, well, if you release that data to public immediately, this proposer from maybe a small liberal arts school in rural Pennsylvania with not a lot of money for it, not a lot of people to support it, they might be slower to write a paper than I don't know, like some smarty pants at Johns Hopkins,
Yeah,
who
exactly.
has 10 people who are itching to get on their names on papers and just will like throw throw their time to get it done in an app, get it done in a weekend,
Yeah.
uh, and so it's just to protect the little guys, and we've found that the community likes it, and we're not stifling scientific progress too much by just having a 1 year proprietary period. But the
Yeah.
Roman for these surveys won't have that at all. It's like as
Gotcha.
soon as it's downlinked and through the scientific processing pipeline, it's public. So we're expecting from downlink, you get about 48 hours of it just going through its various stages of being cleaned up,
Yeah.
calibration, etc. And then it's out the door, ready for anyone.
That's awesome.
Yeah.
That's so cool. Yeah, and I mean, and it makes sense because like the amount of not only the amount of data, but the amount of like we said area that you're covering is just like so many people could work with this, and it's like there's no reason to like there's no specific proposal thing, so it makes sense to just have
Yeah.
it
Yeah.
ready to go.
We do have some time blocked out for general astrophysics
Okay.
inquiries, sort of the same proposal work.
Mm-hmm.
And so for those, we still don't expect to have a proprietary period,
Yeah.
but I don't think it's fully decided. I'll be honest. I have to
Okay.
maybe I should ask my coworkers.
Have have those been chosen yet, or is it gonna wait until launch and then?
Just last week,
Oh,
we
really?
released our first call to proposal
Very
for
exciting.
Roman Space Telescope. So, yeah, if you have an idea and you want to put it on our telescope, now's a great time to start submitting that.
Yeah. Nice. Very cool.
um,
We do have a question in chat going back to some of the dark matter and gravitational lensing and such. Wow, what Crest was wondering, Mom was wondering, what's the biggest falsehood or like maybe misconception about dark matter? Um,
Yeah, I mean, I think the biggest, we'll say, perception that might not be true is that if we find out more information, it might not be that it might not be that exotic of a material.
mhm.
I feel like people uh, are borrowing from their image of like antimatter a lot when they're thinking of
Yes.
dark matter.
Yeah.
I think that isn't like true necessarily. It might be baryonic matter that just has certain properties. So what I mean by baryonic is just like normal matter that has special properties. That's probably that's my instinctual answer without thinking about that question too hard. I think is
Yeah.
that it could just be normal matter, or it might not exist. That could be another misconception about it. that we just got it wrong a little bit.
Yeah. Yeah, it's like I mean, I don't know how long I suppose it'll take to find stuff. I feel like it'll be relatively quick once Roman starts working, but I could just see in like what year and a half, there's papers coming out of like we were wrong or we were right, and both are very exciting. Yeah,
Fight each other.
yeah,
Right, because and I think if I'm not mistaken, dark matter was postulated because they're like these large galactic structures that were sticking together in ways that the normal theory of gravitation would suggest they couldn't.
yeah.
And so
And there had to be something else
got to be
there
something
or
else.
something else
Well,
going
let's
on.
call
Yeah.
it this unobservable matter,
Yes.
dark maybe,
Yeah.
because it's not light.
Exactly. What can we call it? We can't see it, so it's dark matter.
Dark,
Yeah.
literally though.
Yeah. Did you want to talk a little bit about? We mentioned it briefly, but the other instrument that's on the
Yeah.
telescope. Oh, I slid through a bunch of stuff.
Yeah, so we have been talking about the wide field instrument, which is going to be the workhorse
Yeah.
of this telescope. It's going to create about 20 petabytes of data in 5 years, which is
Absolutely
ridiculous.
insane. Absolutely insane.
um, but we have a secondary um, Class D sort of a technological demonstration instrument on board, which is a fancy coronagraph instrument, or
Yes.
bialytic. Um,
Oh, gotta go. All right. Bye.
yeah, yeah,
Um,
yeah.
but
Let's
yeah,
let's go to
is
let's
it
go to the
8?
previous chart, uh, sort of on the right side.
Oops.
Uh,
Oh, okay. I see. I zoomed in too much. Hold on one second. Sorry.
this is about the zoom level we expect to get for
Yeah, right. Um, so oh my god, everything is movable and it's driving me
everything is moving.
insane. So sorry. Okay. So
Looking at chart eight, the
uh,
previous chart.
yeah, chronograph instrument slide. Yeah.
Yeah. So I don't know how much you folks remember about light, but it has wave-like tendencies. And so this chronograph instrument, a typical chronograph is one that has like a physical block between the camera and the star that it's observing, a physical block to observe nearby phenomena.
Mm.
For the sun, for our sun, for example, that might be the actual corona, which what lends itself to this instrument's name. It might be, the upper atmosphere instead of the core of the sun, which is tremendously dimmer than the actual sun. If you remember the eclipse, when the moon acts like a coronagraph and blocks out the star, our sun, you can see structures that you would never be able to see unless it happened.
Yeah, I feel like the very common image that at least I think I've seen so many times with a good example of a chronograph is the when there are solar flares, and
Mm-hmm.
it's like the sun is fully blocked out, and so you can actually
Yeah,
see what else is going on.
yeah, like yeah, exactly.
Yeah.
Um, and so the traditional technology is to put a physical stop, just like a piece of ceramic or a piece of metal along the path of the optical path is what it's called,
Hmm.
the path of light through the telescope to the camera in the back. Just put something that's not translucent in the way, something that's opaque.
Yeah.
This chronograph is quite fancy. It has its nearest neighbor is like adaptive optics, but
Okay.
what's going on is that this camera, which I've shown in the top of the slide there, has a bunch of pistons in the back um,
Okay.
to deform the mirror forward and backward. On the normal of the surface, forward and backward on the scale of nanometers,
Oh my
tens of
god.
nanometers. Yeah, yeah. The surface area of the piston is about a square millimeter, and the deformation forward and backward is about on the scale of nanometers.
Oh my god.
And if you remember much about light, especially in the near infrared, we're talking 1,000 nanometers, 800 nanometers, something in that range.
Hmm.
And so what we're trying to do is we're trying to coerce the star's light to destructively interfere with itself.
Okay.
As opposed to a physical block, the light itself is going to be coerced to cancel itself out and
Yeah.
preserve the nearby objects.
Oh my god.
Yeah, wild.
That's so.
And we expect to get a 100-fold improvement over a traditional coronagraph, meaning we can see objects that are 100 times dimmer than we would with a typical instrument.
Yeah.
Um,
Oh my
we've never
God.
done it in space. We don't know if it's going to work, but we clearly it's going on in a spacecraft. It has 90 days in the first 5 years to prove itself.
Okay.
Uh, but it's not going to be able to be tasked by the public. It literally is just a technology demonstration,
Got you.
right?
Okay.
But the idea, always looking toward the future,
Yeah.
is that we would fly a similar instrument if this goes well. In fact, if it goes really well, we would fly a similar instrument on the Habitable Worlds Observatory slated for 2045 or so.
Oh,
Uh,
okay.
this is like building up to that,
Yeah.
uh, which is
That's
so freaking cool.
yeah. And is it a special type of glass, or is it like extremely like fine individual pieces of glass that allows it to flex like that, or is it just like
It's just deformable.
it just okay.
Yeah. And it's
I
not
guess at
glass,
that level it's
it's
like
a reflective surface, not necessarily
oh, it's
glass.
reflective. That's fair. Yeah.
And nanometers is such a small, you're right.
Exactly.
Nanometers is
Yeah.
such a small way to form it. Yeah,
Yeah.
granted, it might be metal. Something that reflects infrared very well.
Yes.
maybe it's beryllium coated in something clear, or
Yeah. So the image underneath it where it says surface optics, that's like
yeah,
actually that can
that's
be
them.
created.
They could have said "Hi, Mom" instead. They were. This is
That's
them messing around and like showing the deformation. If you zoom all the way in, I don't know how zoomed in. I'm not watching. Yeah, you can see the scale to the right of the image. So that's
oh
100
yes.
nanometers. So yeah, from brightest yellow to darkest blue is, I don't know, 800 nanometers, about 1 micron, a little
Wow.
less than a micron. Uh,
That's crazy.
yeah,
That's so
it's
interesting. Yeah.
so cool. And so, yeah, going on to the next chart, which is what you pulled up first, this is what we're
Yes.
expecting to see is sort of the two the two columns on the right side are what we're expecting to have a result as.
Oh
So the
wow.
two columns on the right side, the far right column is the like quote source in the simulation, and then adding in all the different noises and processing it is what you get in the sort of second to far right column.
Oh, okay.
So after all the calibration is said and done, you can sort of convince yourself that there are like bright blobs near the quote sun in the third column from the left
Yeah.
circles.
Yeah, but it's okay. That's really cool. Wow.
Yeah, yeah, yeah.
That's awesome.
Um, One thing that Dr. Roman, in all of her wisdom and eminence, really made sure to do was transition early telescopes off of film and
Mm.
onto charge coupled devices or CCDs, that sort of camera.
Yeah.
So you could downlink the data instead of having
Thank
to like
God.
read out film,
Yeah. Gotta go
drop film
develop
canisters
everything.
and
You
develop it.
gotta
Yeah,
imagine if Hubble was imagine if Hubble was on film. It was just like we just have to send. We're gonna okay. We have a device and it's going to package up the film and it's gonna send it back to Earth
just gonna
every
drop it
week.
down. Yeah, she was, trying to put Kodak out of business, if you will. uh, and so the this chronograph instrument uses like an evolution on the CCD called an EMCCD or an electromultiplying CCD to
Okay.
really like ratchet up the signal to noise ratio.
Hmm.
And then the WFI uses a CMOS, which is like a coupled complementary metal oxide substrate. I don't know what the acronym stands for. It's something like that.
I've heard it so many times before, and
Yeah.
I'm like I don't know what it stands for,
Sort of
but
like same results, different underlying principles.
yeah.
um, but yeah, you could think, Dr. Roman's direction of funding into development of CCDs and the development of being able to downlink that data for the popularity of cameras today.
Yeah. It's exciting. So we've talked about a lot
Yeah.
of the science stuff, a lot of the development and everything like that. And you mentioned it is the launch as far as, from where it started in the decadal survey in what you said, 2010.
2010.
The launch
Yeah.
is quite close, relatively
It's
speaking.
so close. Yeah, the original launch date was slated for October, but in a freaking absolute miracle, we're moving up the launch date by a month. So
That's
we're expecting to launch in September. We're
that's
like,
crazy.
well, we'll be ready if we cut this one corner and we're fine with that risk. Let's get it launched.
Yeah, that's awesome.
Wild, absolutely wild. So September 16 or 18 is the current estimated launch date,
Very
and
exciting.
we are really, really all hands on deck right now. It is fully assembled in the clean room at NASA Goddard.
Oh,
If
yes.
you move over to chart 3, I took that picture um, maybe 2 weeks ago.
There it is.
Look at it. Look at it.
Wow, that's
Yeah.
exciting.
It's
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 crazy too because like I feel like a lot of times with space telescopes, especially, you don't get scale in photos, and then you see people
losing.
next to it, and you're like, oh my god, that's
We're
huge.
putting that into space.
Yeah,
Yeah.
going into space.
It's
That's
it's
awesome.
going into it's going around Lagrange point 2, so it's going to be hanging out near James Webb,
Okay.
and I think Euclid or whoever's out hanging out there.
Yeah, yeah.
Just going into what's called the libration orbit, and it's being launched on a Falcon Heavy.
Okay.
I think the two side boosters are going to be landed on a barge, and then the middle one is expendable, and this is the first expendable Falcon Heavy in a while.
Huh.
Um,
Okay.
just because we need more loft to get it out to 4 times the distance of the moon.
Gotcha. Fair. Yeah.
Yeah, but we're very excited. I don't know if you're like familiar with SpaceX's product, but they're really good at what they do. They just
Hmm.
like they'll drop your telescope on a dime, and
Yeah.
so we have like two mid-course corrections, and then an orbit insertion, and like we're talking about maybe not needing the first two corrections and having to do just like a 1/3 scale orbit insertion burn.
Oh wow.
Like that is as good as we're expecting to potentially get. Although we're like obviously being able to handle all the cases
Yeah.
should they
Of course.
arise, but we're like
Yeah.
so maybe the like delta V thrusters will in the end be vestigial, and we'll just be like not using them at all.
Yeah.
Wild.
That's crazy. That accuracy is insane. I mean, they have a lot of really great scientists working at
Yeah, a
that
lot
place.
of smart cookies in that team.
Yeah. And so how long until like what's the plan? Because I obviously JWST was different beast of the whole like unfolding and everything. How
Yeah.
long like what happens once you guys reach the Lagrange point and like how long until first light and everything and like first data collection?
Yeah. So we launch. That's T+0. Commissioning lasts 90 days. So it starts from T+0. There is no sort of wait period necessarily.
Gotcha.
And then orbit insertion is scheduled for 120 days.
Okay.
So we will be collecting science before we're even in our final orbit. Is the idea?
Okay.
Uh, yeah, we're very
Nice.
excited. So it's kind of silly. The last week, 2 weeks ago, yeah, when I see this picture, I was on site doing like a tabletop review of the commissioning timeline. So we're just like, all the interested parties are there. You have the comms folks, you got the instrument folks, you have and everyone else.
Yeah.
Um, and it was just like going step by step through the commissioning process for the 90 days. Um, and it was kind of silly, like the like last well, it was separated into like 3 or 4 different segments for commissioning because I don't know how familiar you are with satellite commissioning, but you basically like turn the bus on first. Satellites are thought of in maybe 2 segments. There's the bus, and then there's the payload. So turn
Okay.
the bus on first. That means open the solar panels, turn on the communications devices, open up the sun protection shield, and all the
Mm-hmm.
good stuff.
Yeah.
Um, and then after that's all done, then you move on to the payload and start doing all the checkout. There's like a bake out period as well where we make everything really hot to try to get all the water vapor out or all the
Oh,
other
okay.
gases out. So, but anyway, it was very silly because like this last, I'm going to use the word tranche of days. It was about 35 days, and they were like, first 4 days for WFI. After that, the wide field instrument is done. The remaining 30 days for the chronograph instrument. And I'm like, man, we might get the axe. I don't know if that's going to survive. But because it's during this period where we'll have 24/7 operations support.
Yeah.
So I'll be working midnights.
Oh
Might
man.
work a 7 p.m. to 7 a.m. shift to support this.
Yeah.
I'm happy to do. We're changing the understanding of the universe. I think some sleepless nights are a fine request.
Yeah. That's
Um,
awesome. It's so exciting. You get to be a part of it too. It's just like, you
yeah,
know, it just. I mean, every telescope launch is like a once in a lifetime unique thing, but like also every telescope launch is so special and so exciting, and like it just the I don't know. It's so exciting. It's so cool. I can't wait to see what the Roman's gonna like tell us
yeah,
about the universe and everything.
absolutely. It is very exciting, and yeah, you don't get flagship telescope launches every day.
Yeah.
So to be a part of it is a little humbling, honestly.
Yeah. It's really cool.
um,
How big is the team on Roman? I'm sure it's like kind of like where does the team start and end kind of thing might be sort of
yeah,
iffy,
um,
but
maybe the very last slide
very last
uh,
slide. Okay.
has a sense for like how distributed the team is, but it's not going to be. I don't think it's going to end up looking too great on yeah, maybe the names aren't specific, but you get a sense for like it's all over the place.
Yeah.
Uh,
Lots in the US. We got a bunch of stuff in the EU. Australia's in here.
mhm.
And then is that Japan
Japan, yeah,
as well? And Hawaii.
yeah.
That's
So for
awesome.
Japan and Australia, that's primarily the ground segment, the receivers on the ground, and part of our contract was to like give them funding to upgrade the receivers because we're just going to be inundating them with data.
Yeah, fair. Hey, can you receive like just an absolutely absurd amount of data like all the time?
Yeah, like, are you
No.
asking like our total bandwidth or the bandwidth that we're going to be giving you?
Yeah.
Because we have other clients, you know.
Yeah, yeah. It can't just be
uh,
you.
if I had to give like a wag, just a guess at as to how many folks are on the project, maybe 8,000 people
Oh
all
wow.
is my guess. I don't.
That's awesome.
That's my gut feeling.
Yeah.
It might be wrong, but that's like the scale. Like, people are talking that I've never met before in these meetings, and they're like, "Oh, okay, that's what you're responsible for. I've seen your name on papers, and now it's good to meet you." Well,
Yeah,
this is
yeah.
our.
That's really cool. Just such a yeah. I love that science is one of those things where it's almost always a like a global effort, um,
Yeah,
and it's really cool to have this many people coming together to make such an amazing instrument.
yeah.
Um, are there? I saw that we have a lot of other slides. Are there any other things? We're getting towards the end of time, but like any other things you want to talk about with the Roman or just with astronomy stuff in general? Um,
Yeah, maybe slide 27.
27.
Yeah, I want to talk about exoplanets because
Yes.
that's my favorite region of a topic in this astrophysics. And
Hell yeah.
so the Roman is well postured to detect um, types of exoplanets that we haven't really seen before. So especially these further out orbital distances and larger exoplanets. Because of like gravitational lensing and just this ability to be persistently looking at this region of the sky. So both the time domain um, and sensitivity aspects. But the one thing that I don't think is represented on the slide super well is that we'll be able to detect like rogue planets, and we
Oh,
expect to find not just exoplanets, but exoplanets that have been ejected from their star system. And I
yeah.
think they might be
That's.
boring, they might be like not very active or
I
frozen,
mean,
but
I feel like
it's
just
cool.
inherently with them being like exoplanets that have been ejected from their system, that seems quite interesting.
It's interesting. Yeah, exactly,
Yeah.
exactly. And like we're if we can characterize them, maybe we know more about the universe than we did before. Certainly, and like I think about how we've had three interstellar comets, sorry, interstellar objects. First two at asteroids. Second, third one may be a comet and not an asteroid. Um, and like three of these objects from generic regions of the galaxy have taught us so much about so many things,
Yeah.
and to be able to see like larger objects that are the size of planets, for example. Maybe these were never part of a star system. Maybe these formed in planetary nebula that didn't have a star or something. I don't know,
Yeah.
but we're just going to learn so much. And then yeah, so this chart sort of shows uh
I
this the
just
blue
read
area
the.
is a
I
cutout of where. Go
got
ahead.
you. Sorry, you can keep going.
Oh yeah, the blue region is sort of like the simulated area where Roman's going to be able to make these detections.
Got you. Sorry, I just read the second bullet point. The current count of exoplanets is around 7,000. Roman's expected to reveal 100,000. What do you mean? That's
Yeah,
crazy.
yeah.
Oh my god.
Yeah,
I
if
mean,
you
I
want,
guess that's what you
okay,
get with a survey telescope, but like, Jesus
absolutely.
Christ.
Yeah, okay. Last slide, very last slide, slide number 30. This is
Yes.
just like this is the one other sales sheet, if you
Oh,
will.
yes, yes.
Um, just just a crap ton of stuff that we that we're still interested in figuring out. We have, I don't think we've really seen.
80,000? Sorry.
Yeah,
Go ahead.
yeah, yeah. I don't think we. One of the things I'm excited for is that I don't think we've really confirmed the existence in a sophisticated way of stellar-sized black holes.
Yeah,
I'm excited to have that be a part of the legacy of the Roman mission.
that's exciting. Yeah. Oh, wow. Billions of galaxies, 100 billion stars.
Ridiculous.
Forming planetary systems, too. That's exciting.
Yeah,
That's
yeah, yeah.
wow.
Um, I think we've like made measurements on like only 2% of the stars in the Milky Way. Like we
Yeah,
have astrometry.
yeah. Just that wild, like, oh my god, yeah, we have all this data and we've done all this stuff and we've had this field for so long. I mean,
We're going to
relatively.
double it in the first 6 months or more.
Exactly. Yeah.
We've been doing it for 40 years or whatever it is, but
Yeah.
we're going to go gangbusters on
We're
this
gonna
thing.
go blow everything out of the water.
Yeah, yeah, yeah.
That's awesome. That's so exciting. Oh my gosh, it's gonna be great. I feel like too the Roman like within within the science community, I feel like it has had the hype that it deserves. I hope
Mhm.
at least. But like the public needs to get more on how exciting this is because everybody was super into JWST, also probably because of the sticker price. But
The sugar
like
price
that's
and the risk and the
and the
perceived
risk,
like,
yeah, the whole
yeah,
like
it was a
what if
spectacle
it
because
doesn't
it was
unfold?
so primed to fail, and then it
Exactly,
didn't.
and it didn't.
Yeah, yeah.
God forbid the Romans a little safer, and then no, less people are interested. But like this is like just as groundbreaking and like revolutionary in the field of astrophysics, and I'm just so excited to
Yeah.
see what it does. I hope more people start talking about it too. We're gonna talk about it more as we get closer to the launch and everything.
Yeah.
But
I mean, happy to come back on and talk about it.
yeah, absolutely, we'd love to have you back on. It's great chatting with you.
Yeah,
But yeah, I know you have to get back to your work day and everything. So and back
yeah.
to Pablo. I don't know where you
Back
went,
to
but
Pablo. He's in his crate. We have like a snuffle mat for him, so like we have a bunch of food hidden in like
yeah, and
crevices.
like the fake grass or
Yeah,
something. Yeah,
yeah,
yeah.
yeah. So he's like
Oh,
really going at it. We
so
call it an
cute.
enrichment activity.
I love it. I love it. But yeah, thank you so much for being on and for chatting with us today. It was
Thanks for
lovely
having me.
to have you and to catch up and everything. It's been a
Yeah,
minute. But
Pablo says bye.
bye, Pablo. And yeah, I'll do my normal outro. But as far as the rest of the week goes, this is our last week where we're going to be on for this year, I guess. So on Tuesday, tomorrow, I will be back here with the rest of the D&D squad. We'll be playing more Dungeons and Dragons in Space, and then on Thursday, I'll be here doing something. Maybe we'll play more of that very relaxing. What is it called?
Oh,
Tiny,
what is it called?
tiny glade, or something. Or I'll find some 2 hour long Christmassy game to play. but but yeah, we'll Grant's got all the stuff in the chat already. Thanks again, Sig, for being here. Really appreciate it. It was great
Yeah, thanks
talking.
for having me.
And yeah, we'll have you on again for sure. We'll figure out another time. Love to have you back. And I guess we'll see y'all next time. Bye, everyone.